we talked about atoms. We talked about the electrons, i.e. the outer part of atoms. So now, naturally, we talk mostly about the nucleus. Now, why is atomic mass related to the nucleus? Well, it's mostly in the nucleus. The electrons account for a very small fraction of an atom's mass. So, on the subject of isotopes, so same number of protons, same number of electrons, different numbers of neutrons. The question is, do they behave differently? Like say lithium-6 versus lithium-7, or U-235 versus U-238, or U-233, or any of the ones in between. So do they behave differently? Well, they do, slightly. I mean, under the kinetic molecular model, in which we'll talk about soon enough, of reactions, these heavier ones react slightly slower than the lighter ones do. Why? Because temperature is a measure of average kinetic energy. And if you have more mass, then your V squared, if you did physics, you'd be aware of this equation. Kinetic energy is equal to 1/2 mv squared. So, if you have more mass, 1/2 mv squared. More mass means less speed. Now, if you have less speed, do you crash into other particles more or less? Less, clearly. So if you crash into other particles less, how many chances do you get to react? Less, right? Like less than if you were faster. Now, another thing is that when you have a fusion, i.e. you have a vacuum chamber here and a very small hole and a chamber of gas here. Vacuum. This effusion through this very small hole is faster for lighter isotopes. This is how they enrich uranium to make the first atomic weapons. Because uranium hexafluoride, or U-235, was faster in effusing than uranium-238. So through many cycles of enrichment, they managed to concentrate the U-235 enough to actually use it. Now, this here, this is why you see something like 35.45 under chlorine. Chlorine has two main isotopes in nature, Cl35 and Cl37. This has approximately 35 for its atomic mass. This has approximately 37. What sort of abundances make it so that the weighted average comes out to 35.45? Well, there has to be about 22.5% of this, and the rest is Cl35. Now, how do they actually analyze these? Well, they use a mass spectrometer. So this thing, you take a sample gas, you inject it here, it gets accelerated through metal plates, and there's an electron gun that ionizes the gas. And by here, it's an ion beam. So passing ions, charged particles, through a magnet makes it exert a force on these ions. Now, you learn this in physics. So if you exert the same force on each ion, because they have the same charge, and approximately the same speed, well, this is mostly for the heavier ones. I mean, if you have lithium-6 versus lithium-7, the speed is appreciably different. But the point is, they behave differently, and thus they hit the detector plate in different positions. So if they hit the detector plate in different positions, well, you can measure how many hits there are of each, right? So that gives you the isotopic abundances. Now, Of course, speaking of isotopes, we can't avoid talking about radiation or radioactivity. Why? Because we've all heard about carbon-14 dating. Does it take extra effort to make the carbon-14 decay? No, it decays on its own. It's spontaneous. And it disintegrates to form nitrogen-14. How does it make nitrogen-14? Well, it has to throw off an electron. Why does it have to throw off an electron? Okay, so we start with 6 protons and 8 neutrons, and we want 7 protons and 7 neutrons. So one of the neutrons has to transform to a proton. By conservation of charge, that means it has to throw off an electron. Now, nuclear radiation can be stuff like electrons, or it can be other small particles, i.e. alpha particles, or positrons, or it can be in the form of just energy, photons, as in gamma rays. So these are emitted from the nucleus of a radioisotope as it decays. Well, to say that gamma rays are emitted from the nucleus as it decays is not quite accurate in one sense. Why? Because it goes from being an excited nucleus to a non-excited nucleus, or a less excited nucleus. Well, does that actually change what isotope it is, or what atom? No. So to say that gamma rays come from radioactive decay, well, it depends on your definition. However, most of us agree that we might as well use it because this is often occurring immediately after alpha or beta decay. So why not? An alpha particle is a helium nucleus. So this entire thing is too massive. Alpha particle equals 2He, 2 plus. So the entire nucleus is just too massive. It's just too big to hold together properly. So it just throws off a chunk of protons and neutrons. Now, a beta particle is when it decides, oh, we have too many protons and not enough neutrons, or too many neutrons and not enough protons. And what happens when it's not stable? It goes towards the nearest stable state by throwing off either a positron, thus turning a proton into a neutron, or an electron. Now, there are 2 types of beta decay. Beta positive equals positron, and beta negative equals electron. Remember conservation of charge when you're considering which type happens. Now, you probably see this. Okay, so you're probably wondering what these are. Well, helium nuclei, they can pick up electrons as they travel. So what is helium? Helium is a gas. So what do you need to block the flow, the direct flow of a gas? A few sheets of paper will do. Paper. What about beta particles? They are basically electrons or anti-electrons. Because positrons are anti-electrons. You've heard of antimatter, right? Yeah, this is it. So, what do? Well, paper will not stop electrons very well. I mean, if you've ever thought of insulating yourself from a lightning strike by several stacks of paper, well, no. So, what do you think will insulate you? Well, we know that when lightning strikes a car, it flows into the car's frame and around the passengers without going through the passengers, right? So that's like a Faraday cage of protection. Now, of course, your tires are probably melted and scrapped, but hey, better than you, right? So what does this have to be? This is metal. Even aluminum will do. And gamma rays. Well, what do we think of the most when we think about radiation shielding? Gamma rays are the most dangerous, so they're the most important for radiation shielding. We think of lead. So, lead. Some gamma rays can penetrate up to a few centimeters of lead, so be sure to use enough. Now, gamma rays are above X-rays on the electromagnetic spectrum if you're going for energy being above. The wavelength is smaller. So, what do we call isotopes that emit radiation? Well, we call them radioisotopes. Why? Because initially, when they were dealing with these things, well, I guess scientists like to leave radios in their lab, and so they decided, hey, wait a second, why is there so much static? And radioactive just means it has the potential to emit radiation upon decay. This is not to say that it has to be dangerous. Why? You're breathing in carbon-14 all the time. Yeah, it's radioactive, okay. Is it actually dangerous? No, not functionally. Although the shorter the half-life is, generally the more dangerous actually ingesting or inhaling it is. On the other hand, the shorter the half-life is, the less you're likely to get. Why? Because it already decayed. So, of course, we talked about isotopes, we talked about radioactivity, and now we have to talk about the third thing in the section title, which was atomic mass. Now, this is the weighted averages of the masses of all the naturally occurring isotopes. Okay, what do we see here? For the first time in our Chemistry 11 videos, we have an example. Now, in future questions, we'll have lots of examples. But for now, we only have one. So we have to calculate the atomic mass of each of the following elements given these naturally occurring isotopes and abundances. So for neon, we have we have 20. We can just use 20. It's a good enough approximation. 0.905. So what is a percent? It means divide by 100, right? So 90.5% means 0.905. 100% means 1.00. All right, now that we've cleared that up, plus 21 times 0.3% is how many? 0.00. Okay, this is the units digit of a percentage, and then 3. Plus 22 times 9.2%, that is 0.092. So this is equal to a reason to use our calculators. 20 times 0.905 plus 21 times 0.003 plus 22 times 0.092 is equal to approximately 20.187. Now let's think for a moment. Does this look reasonable? Well, 0.3% is really small compared to these two, so we only really have to think about these two. So let's say all of it is initially neon 20, and then we turn 9.2% into plus 2. So what is that? That's 20 plus 9.2 times 2. So that would be 0.18, what? 184. So the fact that we got 187 here, oh wait, look, 0.3%, so that's 1,000. Oh, that's 3,000. And this is plus 1. So, okay, our answer is reasonable. Now, okay, technically this is not an approximation. It is an exact. But the fact that we approximated the 20 and 21 and 22, well, okay, you can probably get away with putting an approximation. And of course, because this is a word problem, we're supposed to put a statement. And that statement is neon average weight, or average mass, depending on how your teacher prefers to write it. For some odd reason, even though mass and weight are very separate concepts, they use it interchangeably when they're talking about atomic mass unit, atomic weight. Oh, as another note of warning, teachers in chemistry are usually not very strict about grammar. So, depending on whether or not your teacher also teaches English class, you may have to put neons. So for titanium, we have 46, 7.9%. That is 0.079 plus 47, 7.3% is 0.073 plus 48, 73.9% is 0.739, and 49 times 5.5%, 0.055, plus what? Oh, 50 times 5.4%, 50, and then 0.054. If you are not sure your calculator can handle doing all of this at once, feel free to multiply the steps out and then add them up. So, you can also notice something here. What can you notice? Well, you can play the compensating thing, which is that this is, you see that it's centered around 48. Well, then this is minus 2 times this much, and here's plus 2 times this much. So, technically, you can cancel some of it out. And to cancel it out, you would have 46 times 0.079 minus 0.054. The thing is, many teachers do not like this if you just use a calculator and finish it. So if you do not have a calculator, this is a good way to speed things up a little. If you have a calculator, skip this step. If you have a calculator, which you should. In every science class, you should have a calculator. So instead, you end up with brute force, which is 46 times 0.079, that's 3.634, plus 47 times 0.073, 3.431, plus 48 times 0.739, 35.472, plus 49 times 0.055, 2.695, plus 50 times 0.054, 2.7. The main reason why brute forcing it, if you have a calculator, is much better than taking this workaround is because there is no guarantee that your teacher is going to figure out what you're doing fast enough. So, I mean, unless you write explanation phrases, in which case you might as well have just done it the long way anyway. Plus 2.695 plus 35.472 plus 3.431 plus 3.634. Now, I don't need to tell you that they typically use computers to do all this. titanium averages is 47.932 U. So we ended up with a little bit under 48, which is perfectly expected given that we were basically dealing with 48 plus -2 times this, plus -1 times this minus that. Now, the alternative method looks exactly like I just described, which is to say that or 48 plus -2 times 0. There is no guarantee, though, that your teacher is going to understand what you're actually doing unless you explain it in words. Plus -1 times, what was it? Oh, wow. Scrolled down too soon, I guess. 0.073 minus 73 minus 0.055. This is what? This is 48 minus 2 times, oh, what's this? This leads us to 0.025. So times 2. Of course, you can write it all out, but 0.05. And there, 0.73 minus 0.55 is, well, that's 0.018. So this must be equal to 47.9 something. Well, 68 gives you 32 U. So the same thing. Now, of course, this is faster if you don't have a calculator and slower because you actually have to explain what you're doing than this if you do have a calculator. And in summary, elements can exist as a variety of isotopes. They will have essentially the same physical properties, and the chemical properties will only differ very slightly. Now, isotopes are atoms of the same element, and they have different numbers of neutrons. What does same element mean? It means same number of protons, same number of electrons, right? Well, maybe not quite. Why? Think of dealing with carbon, oh, well, okay, oxygen is probably a better example. Oxygen 16, 2 minus, versus oxygen 18. Not exactly the same number of electrons, are they? But they are different isotopes. Or rather, one is an ion, and they are different isotopes. So that's kind of cheating. So teachers will not give you that sort of trick question on a test for the most part. So if they're unstable, we call them radioisotopes because they are radioactive. Why were they called radioactive? Because somebody put their radio too close to their sample and discovered that it kept on getting interrupted by static. Now, during decay, they produce other elements, radiation, and energy, not necessarily in any particular combination. Why might this be the case? Well, gamma rays are energy and radiation, but you do not produce another element when you are producing a gamma ray. You are going from an excited state to an unexcited state. No change in element, right? Now, there are 3 types of radiation produced, and we deal with alpha radiation, beta, and gamma. Now, beta technically has beta positive and beta negative, so it's arguably 4 types of radiation, but it is classified as just beta radiation. Why? Because positrons and electrons are antiparticles of one another. Now, what does that also mean? It also means they can be blocked by the same stuff, which is really what really matters when you're doing radiation tests. Why? Because radiation can be harmful. Well, often it is. But a certain amount of radiation is actually necessary. Why? They took some mice. They bred them in a radiation-free facility. What happened? The baby mice were not healthy because they didn't get any radiation from the background. Well, that's why radiation is necessary. It stimulates the immune system, although that may not be a good thing, depending on how your immune system works. Now, the atomic mass for an element is a weighted average of the masses of all the isotopes relative to their isotopic abundances. Now, it's generally listed in the periodic table. Even if you have a credit card-sized little periodic table, as I do, it still does list the atomic masses. It doesn't list the common ion forms. It barely even lists the names. I mean, it just HE or something for the most part. I do not remember if it has names because it was an old card and I had to throw it out a while back. But the point is that all it had basically was the atomic number, the name, and the atomic mass. The other stuff was all stuff you could remember or remember the rules for, like most common charge and so on. And really, a periodic table does not require that much space as the ones you might find in your textbook use. So, that's it for this section. We'll be talking about the periodic table very soon, though, in the next section.